Hi everyone, these are the video notes that we're going to start using this week. So this is notes for the week from January 7th, 2019 through January 11th through Friday. So these notes will be used all week. They are the properties of solutions notes. You already have a copy of these. However, I've added some things to these over the break that we've just come back from. And so I would like you to discard the old version. I know it's a waste of paper, but go ahead and discard those, and we're gonna use these. So here is what your assignment is. This is a 50-point assignment. It's simply to watch this video, make any notes on the page that I make any others that you wish to make, and then I'm going to work a couple of fairly lengthy problems that are in here, and your assignment is to do those. If you simply copy them, great, but I would like you to attempt to try them on your own before you simply copy. Okay, so let's get started. This is properties of solution. So what is a solution? It's a homogeneous mixture of two or more substances in a single phase. It does not have to involve liquids. Air is a solution of nitrogen, oxygen, carbon dioxide. Solder, which is a metallic substance used in electronics, is a mixture of lead and tin. Steel is a mixture of a metal, iron, and a non-metal carbon. So there's various types of solutions, but in terms of the chemistry at this level, we're usually, and in fact chemistry in general, we're usually talking about something mixed in a liquid. It could either be a gas, a solid, or another liquid. Now, homogeneous means it's equal throughout. It's the same throughout. In other words, if you make a solution of lemonade, that would be an example of a solution. If you took a spoonful out and then took a second spoonful out, they would be exactly the same. If, on the other hand, you take a fruit cocktail, which has a whole lot of different kinds of fruit in it, and you take a spoonful out, one time you might get a pineapple, and the next time you might get a cherry or a pear or something else. That's not a homogeneous solution. So solute, there's three terms that really at the center of this. Solute is the component of lesser concentration, and that's what gets dissolved. So when you think of solutions, think of salt water. It's just a simple example to keep in your mind at all times. So the solute in salt water is the salt. That's what gets dissolved. It gets broken down. The solvent is the component in the greater concentration, and that's what does the dissolving. So think of water in salt water. And then finally, the two of them together is the mixture, so that's the salt and the water together. So a little mnemonic, a little way to remember it is that solute is the shortest of the three words. It's 6 letters, and that's salt in this example. That's the thing you have the least of. The thing in the middle is solvent. That's 7 letters, and that's the water. That's the substance that you have more of than the solute. And then when you put the two of them together, you'll have the most of that. That's the solution. That's 8 letters. So it's maybe a little way to help you remember that. Okay, so the first page, let's just go through a few more definitions. Concentration means how much solute do you have in a solution. You make lemonade with a powdered mix, and the concentration of the lemonade mix, the solute, will determine how the lemonade tastes. If you want it stronger and sweeter, you can add more lemonade mix. That's more solute to the solution. If you want the lemonade to be less strong, you can dilute the solution, and that's by adding water, the solvent. By far the most common solvent we'll deal with is water. Solubility is the maximum amount of material that will dissolve in a given amount of solvent. Solubility is affected by temperature and pressure. Molar solubility is the number of moles of solute that dissolves in exactly 1 liter of solvent, and that's expressed in units of molarity. That's capital M, or the use of square brackets, and that is the most common measure of concentration that we will deal with, but certainly not the only one. A saturated solution is one that has so much solute, so much salt in our example, that the solvent can't dissolve it. When there's too much sodium chloride, table salt, there will not be enough water molecules to break them apart, and the granules of salt, which have not broken up, will eventually just sink to the bottom. An unsaturated solution is a solution containing less than the maximum amount of solute that will dissolve under a given set of conditions. Okay, saturated solution. So a solution that has been prepared at an elevated temperature and then slowly cooled. It contains more than the usual maximum amount of solution dissolved. In other words, more of the solute has broken apart and dissolved when the temperature is higher. That's true for most solid substances, though not all. A supersaturated solution is very unstable, and agitation, such as stirring or pouring, can cause those extra, for example, sodium chloride ions to come back together and form a salt crystal again. Another way that can happen is you put a seed crystal in. You put, say, a string that has some salt crystals on it in the middle of that solution, and the sodium and chloride will start to attach to them, and that's called a seed crystal, and that will cause the excess solute to crystallize out of solution, leaving the remaining solvent saturated. Rock candy is made this way. We'll actually do a little project with that. It's kind of a simple project, and acetate in hand warmers and some other things. Okay, so here are a couple more definitions, miscible and immiscible. Immiscible is when two or more liquids will mix. Okay, so salt and water, food coloring in water, those will mix evenly and uniformly and form a homogeneous solution. Immiscible is when two substances or liquids don't mix. For example, oil and water don't mix. One layers on top of the other. And we'll do a little project with that later this week. Now, here are the units of concentration. There's several ways, and the ones that chemists will use just depends on what they're trying to measure and what the constraints, what the limitations of their project are. The most common one that we'll use that's used is molarity, and that's the number of moles of solute per liter of solution. So you see the formula down there, capital M, moles of solute over liters of solution. Be careful of whether the denominator is the amount of solute, the amount of solution or the amount of solvent. In this case, it is the amount of solution. And that's temperature dependent. Why would that be? Well, the liquid solvent can expand. If you freeze water, it gets bigger. So what was 1 liter of liquid water will be more than a liter. The liter is a measure of volume, will be more than a liter of ice. So that would change your molarity simply by freezing the water, even though you still have the same number of water molecules as you had before. That's not a constant ratio of solute to solvent particles. Most molar solutions are made at 25 degrees centigrade. That's about room temperature. So this point is subtle and picky, but it's important. Okay, the next measure of concentration is mass percent. So you could call it mass in chemistry, you can call it weight. We don't make a big distinction in chemistry. So that's simply the grams of solute over the grams of solution. So you can see grams over grams is going to cancel out, and it's times 100%. So the number is going to be, the unit of measure is going to be percentage. Okay, after that we have mole fraction, and that's a ratio of the mole of the substance you're interested in. Now at the beginning, many times we're going to be dealing with just one solute, although you could have more. But it's the moles of whatever it is you're interested in over the total moles in the solution. So if you're interested in the moles of solute, it would be moles of solute over moles of solute plus moles of solvent. That's the total moles of the solution. If you're interested in the moles of solvent, then it would be moles of solvent over, again, same denominator, moles of solute plus moles of solvent. It just depends on which one you're interested in knowing the mole fraction of. Molality. Molality is the number of moles of solute per kilogram of solvent. So notice this time the denominator is solvent, not solution. And we're not dealing with liters, we're dealing with kilograms. That's not temperature dependent, because even if your water freezes, you still have the same mass, the same amount of water molecules. It's the same number of kilograms, although the volume has expanded. Okay, so, and that's keep in mind that molality is measured or is designated by a small m. So moles of solute over kilograms of solvent. And finally, the last one is parts per million, although it could be parts per billion, parts per trillion, like what they use in water purification. And that's simply the grams of solute over the grams of solution times 1 million if you're interested in parts per million. Or if it's billion, you would multiply by billion. Or for parts per trillion, you multiply by trillion. Usually if we deal with this measure, it's used for very small concentrations. We will use parts per million. Okay, here's our first exercise. This is one we have done in class prior to the break, but since it's been a long time and since it's a good problem to review, we're going to do this one again. Now, this is part of your homework assignment tonight, is to do this. We may actually do this one in class, but generally speaking, doing the problems, these sample problems, are part of your homework. This is a really good problem because it's short, but it covers all four of the concentration measures that we talked about: molarity, mass percent, mole fraction, molality. It doesn't include parts per million, but it includes the other four. So let's read it and let's do it. This is going to take a little bit of space, but I think there should be enough space on your note sheet. You can do it there or do it on a separate piece of paper. I really recommend that you try to think about this problem and think how you think you could do it. Don't just copy. You don't learn that way. Try to see if you can figure it out, but don't beat your head against the wall for too long. Maybe what you need to do is see what the first step is, and then see if you can do the second step. If you get through the first two steps, even if you need some help, see if you can figure out the third step. You always want to test yourself and see how much of this problem can you do on your own. And it's a good problem to repeat over and over again. Okay, so here we go. A solution is prepared by mixing 1 gram of ethanol, C2H5OH, with 100 grams of water to give a final volume of 101 milliliters. Calculate the molarity, mass percent, mole fraction, and molality of ethanol in the solution. Okay, so here we go. You see that we're given a number of grams of ethanol and the chemical formula. So the first thing we want to do is let's figure out the molar mass, okay? You know you're going to need that. So we're going to say 1 mole of C2H5OH equals, and let's just work it out. It's 2 times 12.01 grams, this is for carbon, plus 6 times 1.01 grams, that's for hydrogen, plus 1 times 16 grams, that's for oxygen. And when we add all those up, we get 46.08 grams of ethanol. Okay, now we want to find molality. And the way you do this is anytime you see, or excuse me, molarity. Anytime you do this, you want to convert that capital M for molarity into the units that it actually represents. And that's what we're trying to find. So way over here on the right, we want to know how many moles of C2H5OH there are in 1 liter of the solution. Now, I could write for solution C2H5OH plus H2O, but let's just call it solution. And of course, the abbreviation for that is SOLN, okay? So that's what we're trying to find. We're trying to find some number that's going to fill in that blank right there, that question mark, okay? How many moles? The way you deal with these problems is that you basically look at what numbers you're given, and you look at what numbers you're trying to end up with. And you try to just basically play with the units, manipulate the units until you get some way that you have moles of C2H6OH over 1 liter of the total solution. So what are we starting with? Well, we know we have 1 gram of ethanol. Okay? So we need to get moles of ethanol. So the first thing that we can do, well, and by the way, we also know that we have that. We're trying to find liters of solution. Well, we know that we have 101 milliliters of solution. So let's go ahead and write that down here. 101 milliliters. And be sure you put solution, because it could be milliliters of ethanol, it could be milliliters of water. So right now we have grams over some form of liter. Okay, we want to eventually get to liters, we have milliliters. So let's take care of the top first. Let's take care of the top first. So we know our molar mass, that there's 1 mole of C2H5OH for every 46.08 grams. Okay? So grams of ethanol cancels with grams of ethanol, and we have moles over milliliters. So right away, we've taken care of it. We have moles of ethanol on top. So that part's taken care of. Now we have to deal with the bottom part. We have milliliters, but we need to convert that into liters. Milliliters of solution, we need liters. So we need the common conversion of that, and that's going to be 1,000 milliliters, and this is one you should just memorize, for every 1 liter. Okay, and that's milliliters of solution. It could be milliliters of anything. It's true, this relationship is true of milliliters to liters of anything, but we're interested in solution, so we're going to go ahead and write that so we complete our units of measure. Okay, so milliliters of solution cancels with milliliters of solution, so I have moles of ethanol, and I have liters of solution, which is what I want. So all the units line up properly. So now you crunch your numbers, and what you end up with is, take away our question mark, and you end up with 0.215 moles per liter, or you could call it capital M, molarity. Okay? We want to try to find out the mass percent of the solute, that's of the ethanol. And in general, the mass percent is grams, in this case of C2H5OH, over grams of the solution. And since it's a percentage, we multiply by 100%. Okay? So grams of solute, well, that's easy. It was given to us up here in the problem. Okay? So it's 1 gram. And I should be more proper and write 1.00, but let's go ahead. I'm trying to save a little space here. And how many grams of solution do we have? Well, we have 1 gram of ethanol and 100 grams of water. That's the total solution right there, those two things. So it's 1 gram plus 100 grams for the water. And that gives us 1 over 101 times 100%, because the grams have canceled out at this point. And that's going to equal 0.99%. And that's the only unit of measure is the percent. So 1 divided by 101 times 100 will give you 0.99. Okay, next we want to find the mole fraction. It's kind of like mass percent, except it deals with moles. And that's designated by this large X Greek letter, and it's the moles of ethanol over the moles of the solution, which is the ethanol plus the water together. Well, this problem is a little more involved because we got to figure out how many moles of each we have. So for ethanol, we have 1.0 grams over the grams, the molar mass of ethanol, which is 46.08 grams. We're making a mole conversion, so let me change that. So it's times the molar conversion, which is 1 mole of ethanol. Takes a long time to write ethanol every time, but there we go. Over 46.08 grams of ethanol. But get used to doing it because, believe me, it's easy to get mixed up with which substance you're talking about. Okay? And if you crunch the number on that, you get that you have 0.0217 moles of ethanol. Okay, now we have to do the same thing for water. Okay, so we have 100 grams of water. Remember, we're trying to find moles over moles. So we kind of have to do these steps first. Times the molar mass of water. I didn't compute that at the top, but you've done that a lot of times in class. Oxygen is 16. 2 hydrogens are 1.01 each. So that gives you 18.02 grams for H2O. Okay, and you do the number, crunch the numbers on that, and you end up with 5.55 moles of H2O. Okay, now for the mole fraction, we simply take the moles of ethanol, excuse me, and divide it by the moles of water, and that'll give us the fraction of that. Excuse me, take that back. Almost made a mistake. That's very common. You now have to add, in order to have the moles of solution, you have to take the moles of water plus the moles of ethanol. You have to add those together to get the total moles of solution, and then you divide the moles of ethanol only by that number. So it's moles of ethanol over moles of water plus ethanol. So let's go down here and do that. So it's 0.0217 for ethanol. And for the solution, the number of moles is 0.0217 plus 5.55. Okay, and that's going to give you an answer of 0.00389. And that's your answer. And it's a fraction, so there's no units of measure. It's just moles over moles. They cancel out. That's your final answer for mole fraction. Okay? Finally, we need to find molality. Okay? Okay, so for molality, what is it? You go back to the previous page to find out what molality is. And what it is it's moles of the solute divided by the kilograms of solvent. In that case, that's H2O. It's not the whole solution. It's just the solvent, water. Okay? So first thing we want to do is, how many moles of C2H5OH do we have? Well, we already know. We figured it out. Okay? We figured it out up here. It's 0.0217. So already I know the numerator of my answer. Okay? So it's going to be 0.0217 mole of ethylene. Okay. Now what we have to do is we have to figure out how many kilograms of water. Well, we know excuse me. So we know we have that much in 100 grams of water. You go back to the top. There's 100 grams of water. That's your solute. So we have that over 100 grams of H2O. So we're almost to our final units of measure. We got moles over grams of H2O. We need kilograms of H2O. So, and I'm sorry, I was off the page, so let me say that again. We know how many moles. We calculated that up here. And up at the top, you go back to the question at the very top. We know we have 100 grams of water. That's our solvent, not the solution, just the solvent. So now all I got to do is get grams to become kilograms, and there's a simple conversion for that, which again you should memorize. There's 1,000 grams of anything, but in this case we're interested in H2O, for every 1 kilogram of H2O. Grams, H2O cancels grams. I have moles of ethanol over kilograms of water. That's exactly what I want for my final answer. So you crunch the numbers on that, and you get 0.217, and properly that should be written as 0.217 small m for molality. Okay, And that's the end of that problem. I recommend you work this problem over and over because it has four of the major concentration, really the four major ones. Parts per million is not used all that often. Work on this over and over. I would do this 3, 4, 5, to do this once a night until this really comes through to you. Okay? All right. Okay, here's exercise 2. The electrolyte in automobile lead storage batteries is 3.75 molar sulfuric acid. An electrolyte is a solution that conducts electricity. And it has a density of 1.23 grams per milliliter. So the entire solution has a density. That's a combination, by the way, when you have an acid solution, it's in a solution of water. They don't say water, but that's assumed that you know that. So now you do know that. So the density of the entire solution of the sulfuric acid in water is 1.230 grams per milliliter. Calculate the mass percent and molality. Okay, so we're looking for this and this. It's not asking us for molarity or mole fraction or anything else of the sulfuric acid. Okay, so the first thing we want is mass percent. So what we know we're looking for at the end is grams of H2SO4. And you may be saying, oh my gosh, how do I know that sulfuric acid is H2SO4? You'll learn it by the end of this week, okay? Over grams of solution, I could write H2SO4 plus H2O, but we're just going to write solution, SOLN. And then it's times 100%. Okay, there you go. So you need to manipulate the units, the information you have up here. So you end up with grams of H2SO4 over grams of solution. Okay, so we're starting off, the number it gives us to start off with for the H2SO4 is this, 3.75 moles of H2SO4 for every 1 liter of water. That's what molarity is. It's moles per liter. And 1 liter, and I said that incorrectly, it's not of water, it's of solution. And it's important, that's why it's always important to write down what it is after, because you can very easily get confused which one you're dealing with. Okay? All right. Well, what did I say we should always do first? Figure out the molar mass, and I'm just going to shortcut this one. So 1 mole of H2SO4, go ahead and compute that, but what you should end up with is 98.08 grams of H2SO4 for 1 mole. Okay? All right. So we need to have grams on the top here. We have moles over here. So let's take care of the numerator first. We know how to convert from moles to grams. We've been doing it all semester, okay? So what you have is 98.08 grams of H2SO4 for every 1 mole of H2SO4. Okay, good. So now the moles of H2SO4 cancels, and we have grams of H2SO4 on top, which is what we want. Now we need to get grams of solution on the bottom. Okay. Okay, so now we need to somehow come up with grams of solution on the bottom. Now, where in our problem do we see anything that deals with grams of solution? And right up there is the density. It's 1.230 grams of solution for every milliliter of solution. That's talking about the entire solution. So we can put grams on the bottom by taking that and saying that there's 1 milliliter of solution for every 1.230 grams of the solution. Again, the solution is the acid and the water together. Okay, so look what I have here. I have milliliters here and liters here. So we need to convert these milliliters into liters, and it's the same conversion we used before. There's 1,000 milliliters of solution of anything, but in this case of the solution is what we're interested in, over 1 liter of solution. Okay, so look what cancels. Liters of solution cancels with liters of solution. Milliliters of solution cancels with milliliters of solution. And what we have left is grams of solution, which is what we want here. And up on the top, what we did earlier, we have grams of the solute. So when you crunch your numbers, you will end up with an answer that is 29.9%. That's a percent sign. H2SO4. And that's our answer. Okay. It's a little bit complicated. Again, another problem that you should practice until it becomes natural. The whole strategy for these problems is figure out how to manipulate the units of measure so you end up at the end of the problem with the ones you're trying to find. There's no other way to do these problems. There's not some intuitive way you're going to see how these problems work. Okay, next, the problem wants us to figure out molality. So go back and review what is molality. And molality, what you're trying to find, is the moles of your solute, in this case the sulfuric acid, for every 1 kilogram of water. The solvent, not the solution. Okay? Now, this problem starts off really easy, but it gets a little bit involved for the second part. To know the moles of H2SO4, well, that's pretty much given to us. We have 3.75 moles per 1 liter, because that's what molarity means, this number right here. Okay, it's the next number that's going to get a little involved. Okay, so we have to figure out kilograms of water. But we aren't told anything about water. We're told something about the solute, which is the sulfuric acid, and about the solution. We know the density of the solution. How do we figure out how many kilograms of water? Okay, first thing we have to do is we have to figure out how many grams. Okay, we're going to work in grams, and only at the very end are we going to convert to kilograms. So we know how many, we're going to figure out first how many grams of sulfuric acid we have. So let's write this procedure down. How many grams of sulfuric acid, H2SO4? Okay, so there's 3.75 moles of H2SO4 over 1 liter of solution, of the entire solution. And now we use our molar mass conversion that there is 98.08 grams of sulfuric acid for every mole. Every mole has that. That's the molar mass conversion up here at the top. And from that, we can figure out how many grams of H2SO4 there is in a liter, and that number turns out to be 367.8 grams of H2SO4 for every liter of solution. Notice I want to keep liters as my denominator in all of these, so I'm comparing like amounts, okay? So now, what can we tell us about how many grams there are in the solution? Well, it tells us that the density is 1.230 grams per milliliter. But I'd like to convert that into liters because this is in liters. So let's do that. So it's a simple conversion. There's 1,000 milliliters for every 1 liter. So milliliters cancels with milliliters, and you end up with 1,230 grams for every 1 liter. and that's grams of solution. Okay, so we now know in a liter how many grams of solution we have. We also know how many grams of sulfuric acid. So if we take the difference between those two numbers, we'll get the number of grams of water. And that gives us a number of 862.2 grams of H2O. So we're getting close to our denominator, right? We want to know kilograms for our final answer. That's this right here, molality. We want to know kilograms of H2O. So now we have to do a simple grams to kilograms conversion. So we have, so how many kilograms? And we have 862.2 grams. Since I already wrote H2O up here, I'm not going to write it again here, times 1 kilogram for every 1,000 grams. Grams cancels out, you do the math, and you have 0.8622 kilograms of H2O. And that's for every liter. Let's not forget. We made that conversion. That's for every liter, for every 1 liter of solution. Okay? All right. Okay, now we put Humpty Dumpty together. We figured out how many moles of H2SO4 we had. We already knew that. We had 3.75 moles for every liter, and we have 0.8622 kilograms of water for every liter. So if we put those two numbers on top of each other, moles per liter of this, kilograms per liter of this, we'll come up with our answer. So it is 3.75 moles of sulfuric acid for every liter, and that's all over 0.8622 kilograms of water for every liter. The liters cancel out, and you end up with 3.75 divided by 0.8622, and that answer turns out to be 4.35 moles per kilogram, or molal, small m. And that's your final answer. Okay, so we're going to stop right here. We're at the end of page 5 of your notes. And again, we've done these problems before, but it was worth doing them again as a review. We're generally going to try to cover about 7 or 8 pages an evening of the notes. You're always welcome to read ahead. The rest of the notes don't have any really long problems, but I would recommend you work on these problems, and they will really, really help you out. Okay, I'm sorry, we're having a little bit of technical difficulties here. So anyway, we came up with our final answer up here. We'll just write it out. If you want to actually put it back into the original equation we started with, it's 1 liter over 0.8622 kilograms of water. And that gives us our final answer that we stated down below is 4.35 moles of sulfuric acid for every kilogram of water. And that's that. Okay,